So, invariably the transform techniques are useless as far as the time varying systems are concerned. So, the transform techniques, whether Laplace, Fourier or your Z transform or any one of these transforms are only meaningful when the system is time invariant. We still do not know in fact how to solve by any transform technique a time varying systems. We have no transforms available to convert that by using this particular transform into a simple algebraic equation. Okay? At some stage, hopefully, if I have time, I will expose to you to some technique, but they are not very universal technique. But right now, let us assume that the only advantage of doing a transformation of this equation comes only for the linear time invariant system. So, having said that, then I need to find this k has to be removed and put a I here. We will discuss these systems only for transform domain because we can't do it for the other one. In which case, what do I get? I take Z transform. Okay, that is natural transform for this discrete systems. So, I take Z transform on both sides. And what do I get? I get Z transform of xk plus 1 is equal to A times xg plus B times ug. I can do this because A and B are constant matrices. If A is also a function of k, I will say an argument which I told you earlier, the product will give you a convolution, so I can't do much after that. Now, what is the Z transform of k plus 1? This is a bit tricky to, I think you should spend some time to understand that. If this is xk, say this is x0, this is x1, x2 and so on and so on. This is k. Let us assume this is a causal signal because we are already dealing with causal systems. So, this is 0 for less than this and this start to this goes to this value. Now, if I write k plus 1, what do I get? When k is equal to 0, the value here now will be x1. That means this will be shifted onto this side. So, this becomes x1 and this becomes x2 and so on and so on. Okay. Now, I need to find the Z transform of this signal now. This signal at 0 it is x1, at 1 it is x2 and so on and so forth. So, what is my Z? Z transform? Z transform of xk plus 1 by definition is equal to x1 plus Z inverse x2 plus Z minus 2 x3, so on and so forth. Because this is 0, this is 1, 1 means that minus 1, so it goes like this. Now, let me write this as equal to x0 plus z minus 1 x1 plus z minus 2 x2, so on and so forth. Compare this and this, what do I do to get this? If I multiply this by z, I get zx0, x1, z minus 1, x2, all these are same terms. Only thing is I have added now this term, which means I must subtract this term. And what is this function equal to? By definition, this is xz, right? x0 plus z minus 1, x1, so on and so forth. So this function what I wrote here is equal to zxz minus zx0 is equal to this. So now what I rewrite this as equal to zi minus a into xz is equal to, if I bring this on this side, zx0 plus b uz. Okay. So xz is equal to zi minus a inverse into z into x0 plus zi minus a inverse b uz. Now this xz is the z transform of x of k or x of n, whatever it is. This will have two components. One component is the ZIR and this component is the ZSR, and ZIR is given by this term, which if I now find the inverse transform of this, must match whatever I have written here for the ZIR in the case of time invariant systems, right? Let me take up that and see how I manage that. Right? That is the operator on the x0, the matrix operator. So this is equal to z into z minus 1 into I minus a by z to the power minus. So z into z minus 1 cancels, becomes 1. I am pulling out z from here. Z is a scalar quantity. I am pulling out z out of this. I am left with I and a divided by z here, and the inverse remains inverse, and the z pulled out and the outside, both of them will cancel to be equal to just 1, and I will left with this. Okay. This, if you remember, this matrix inversion, we can use exactly same formula as we have for inverse of 1 by 1 plus x. So this will be equal to, this is 1 by something, 1 by 1 plus something. So I can now write the inversion of that will be equal to I plus a by z plus a by z square by factorial 2, no factorial 2, that's all, plus right, so on and so forth. We did this in state variables in 101.